Have you ever looked up into the vast, dark expanse of the night sky? Have you ever felt a sense of wonder, a feeling of being small, yet connected to something immense and ancient? For as long as we have been human, we have looked to the heavens and asked the most profound questions imaginable. Where did all of this come from? What is our place in this grand, silent theatre of stars and galaxies? It is a question that binds us together across time and across cultures, a universal thread woven into the very fabric of our consciousness. This fundamental curiosity is the engine of our greatest discoveries. The desire to know our origin story is a powerful force, a quest not just for knowledge but for meaning. We are seeking the origin of space itself, searching for the moment that time began to tick forward. It is a story so epic, so grand, that it challenges the very limits of our imagination. Yet it is our story. The atoms that make up your body, all of it was forged in the crucible of cosmic events that began billions of years ago. Where did we come from? Our journey is one of time. We must travel backward, peeling away cosmic history. Imagine the universe's history compressed into a year. The Big Bang happens on January 1st. Dinosaurs occupy a few days in mid-December. Human civilization flashes by in the final seconds of New Year's Eve. Our lives are fleeting in cosmic time. The universe has existed for billions of years. To travel back, we rewind this cosmic clock. We go back to the cosmic dark ages. We are heading for the first few seconds of existence. The universe was a place of such extreme energy. The secrets of our origins are hidden. This is the moment of creation itself. When we look out into the universe, we see a breathtaking tapestry of light and structure. Stars gather into galaxies like our Milky Way, one of trillions scattered throughout the observable universe. Galaxies are drawn together by gravity into clusters, forming a vast network called the cosmic web. Tiny fluctuations in the early universe, stretched to astronomical sizes, seeded this structure. Understanding this cosmic tapestry is key to understanding our own origins and our cosmic home. This grand architecture is a fossil record, preserving the history of its own creation for us to read. How can we know what the universe was like billions of years ago? The universe has provided us with its own kind of time machine, ancient light. Because light travels at a finite speed, we see distant objects as they were in the past. Telescopes allow us to see galaxies as they were when the universe was young. Radio astronomers detected a faint hiss of microwave radiation. This is the afterglow of the Big Bang, a relic from when the universe was just 380,000 years old. Known as the cosmic microwave background, or CMB, this radiation is the echo of creation. By studying this ancient light, we are looking at a baby picture of the universe, providing concrete evidence for the Big Bang. The universe speaks to us in a language of light. Every star broadcasts its story across the cosmos. To understand our origins, we must learn to decipher this language. When we pass starlight through a prism, it splits into a spectrum crossed by dark lines. These lines are like cosmic fingerprints that reveal the chemical composition of the star. This technique, called spectroscopy, is one of our most powerful tools. The answer lies in the hearts of stars, giant nuclear furnaces. It is here that the raw materials for life and planets are manufactured. We are, in a very literal sense, made of stardust. The stars are our cosmic ancestors. Our quest to understand the universe is also a story about ourselves. For thousands of years, we could only look up and wonder. But over the last few centuries, a new way of knowing emerged, the scientific method. We built telescopes that allowed us to see beyond the limits of our own eyes, revealing a universe far larger than anyone had ever imagined. Science showed us that our Earth is just one planet orbiting an ordinary star. While we may not be at the physical center of the cosmos, we are, as far as we know, at a center of understanding. We are the part of the universe that has become self-aware. The universe through us is beginning to understand itself. We are not separate from the universe, we are a part of it. We stand at the precipice of a great adventure. We have asked the question, we have surveyed the vastness of time and space, and we have gathered our tools of discovery. Now, it is time to begin our journey back to the beginning. We will leave behind the familiar comfort of our own world and plunge into the chaos and fire of the infant universe. We will witness events on a scale that defies everyday language, where energies were higher and timescales were shorter than anything we can truly imagine. It is a journey into the ultimate unknown, to the very edge of space and time. Our story will begin not with a whimper, but with a bang. We will explore the moment of creation, the Big Bang. We will investigate what science can tell us about that first singular moment when everything we see around us, all of space, all of time, all of matter and energy, burst forth from an infinitesimally small, infinitely hot and dense point. We will examine the evidence for this incredible event, from the expansion of the universe to the faint, lingering glow of its afterheat that still bathes the cosmos today. This is the first chapter in our cosmic story. From there, we will follow the story as it unfolds, moment by moment. We will see how a universe of pure energy cooled and condensed into the first particles of matter. We will witness the rapid exponential expansion known as inflation, which smoothed out the universe and laid the groundwork for the structures we see today. We will watch as the first protons and neutrons combine to form the first atomic nuclei, setting the chemical composition of the cosmos for hundreds of millions of years. We will journey through the long, dark ages before the first light appeared. This is more than just a history lesson. It is a story of transformation, of a universe evolving from a state of perfect simplicity to one of astonishing complexity. It is the story of how a smooth, uniform fireball gave rise to stars, galaxies, planets, and eventually us. The journey ahead is filled with mystery, wonder, and some of the most profound ideas in all of science. The stage is set. The clock is ready to be wound back. The greatest story ever told is about to begin. Let us step into the past and witness the birth of our universe. Our journey has reached time zero. All the matter and energy of the universe is compressed into a point of unimaginable density and infinite temperature. This is the Big Bang, not an explosion in space, but of space itself. It was the beginning of the cosmic clock. Asking what came before is like asking what is north of the North Pole. This is not a point in time, but the beginning of time, the source from which the cosmos flows. Everything has its roots in this extraordinary moment. The next fraction of a second will determine the fate of the cosmos for the next 14 billion years. We are now entering the very first sliver of time imaginable, the Planck epoch. Lasting from time 0 to 10 to the minus 43 seconds, it is a period of time so infinitesimally short that our human minds can barely assign it meaning. In this fleeting instant, the universe was a chaotic, seething cauldron of energy. In this primordial state, the fundamental forces of nature were merged into a single, unified superforce. This is the ultimate wall for modern physics. Scientists call this hypothetical theory quantum gravity. Physicists imagine a universe where space and time themselves were a bubbling, chaotic quantum foam. The seeds of the structured, orderly universe we see today were planted in this unimaginable furnace. These fluctuations, born in the Planck epoch, would later be stretched across the cosmos, providing the gravitational blueprints for the first stars and galaxies. As the Planck epoch ends, the universe takes its first step. At this stage, the universe is a sea of pure, radiant energy. There is no matter as we would recognize it, only exotic elementary particles and photons. The cosmos is a fireball where energy transforms into matter and vice versa. Particles of matter and antimatter are constantly being created. The early universe was a frantic cycle of creation and annihilation. As the universe expanded and cooled, a tiny imbalance favored matter. Every galaxy, star, planet, and living being is made from the matter that survived. We are remnants of a great cosmic battle. As the universe continues its rapid expansion, it also continues to cool. At about 10 to the minus 43 seconds after the Big Bang, the temperature drops just enough for the first fundamental change in the fabric of reality to occur. The single, unified superforce of the Planck epoch can no longer hold together. The first of the four fundamental forces separates itself from the others. Gravity breaks away, becoming a distinct force for the first time. It is a monumental moment. Gravity, the great sculptor of the cosmos, the force that will one day pull matter together to form galaxies and stars, now has its own independent identity. The remaining three forces, the strong nuclear force, the weak nuclear force, and the electromagnetic force, are still merged together. Physicists refer to this state of affairs as a grand unified theory, or GUT. This combined gut force rules the universe during this new era, known as the Grand Unification Epoch. The universe is still a seething soup of exotic particles, including quarks, electrons, and their antimatter partners, but now their interactions are governed by this new, slightly less unified force. We are witnessing the universe developing its fundamental laws, like a cooling crystal forming its structure. This process of forces separating as the universe cools is known as symmetry breaking. Imagine a perfectly balanced pencil standing on its point. It is in a state of high energy and perfect symmetry. But it is also unstable. The slightest nudge will cause it to fall in a random direction, breaking the symmetry and settling into a lower, more stable energy state. In a similar way, the early universe was in a high-energy, perfectly symmetrical state with its unified force. As it cooled, it fell into a new, lower energy state, and the symmetry of the forces was broken as gravity went its own way. This concept of symmetry breaking is crucial to understanding the evolution of the cosmos. Each time a symmetry breaks, the universe undergoes a phase transition, similar to how water turning into ice undergoes a phase transition. These moments are when the fundamental properties of our universe are locked in. The separation of gravity was the first and perhaps most significant of these events. It set the stage for a universe where large-scale structures could form over billions of years, a universe where planets could orbit stars and galaxies could hold themselves together against the rush of expansion. The cosmos was beginning to look a little more familiar. The universe is now about 10 to the minus 36 seconds old. It has expanded to perhaps the size of a grapefruit, but the temperature and density are still beyond all earthly comparison. The cosmos is on the verge of another critical phase transition. The Grand Unification Epoch is coming to an end. As the universe continues to cool, the combined gutty force becomes unstable, just as the superforce did before it. The symmetry is about to break again. In a flash, the strong nuclear force separates from the electroweak force. This is another pivotal moment in the creation of the universe's physics. The strong nuclear force is the most powerful of the four forces, but it operates over incredibly short distances. It is the cosmic glue that will eventually bind quarks together to form protons and neutrons. It is also the force that will hold those protons and neutrons together inside the nucleus of an atom. Without the strong force breaking away and acquiring its unique properties, atomic nuclei could never form. The universe would have remained a soup of free-roaming quarks and other elementary particles. The emergence of the strong force is a necessary step toward the creation of all the chemical elements, and thus all the matter we know. This event, the breaking of the gut symmetry, is thought to have released a tremendous amount of energy into the universe. Imagine a lake of supercooled water, water that is below its freezing point but has remained liquid. If you drop a single ice crystal into it, the entire lake can flash freeze in an instant, releasing latent heat in the process. Some theories suggest that the energy released by this cosmic phase transition was not smooth or uniform. It may have created defects in the fabric of space-time, exotic relics like cosmic strings or magnetic monopoles that physicists are still searching for today. More importantly, this symmetry-breaking event is believed to be the trigger for the single most dramatic period in our universe's history. The energy released by this phase transition is thought to have supercharged the expansion of the universe, kicking off a period of unbelievable exponential growth. The universe is about to go through a growth spurt so extreme it will stretch microscopic quantum fluctuations into cosmic-sized structures, laying the foundation for everything to come. The stage is set for a new era, one that will solve some of the deepest puzzles of the Big Bang model. The era of cosmic inflation is about to begin. Following the separation of the strong force, the universe entered cosmic inflation. Lasting a tiny fraction of a second, the universe expanded by a factor of at least 10 to the power of 26. A region smaller than a proton stretched to larger than a galaxy. This hyper-expansion, faster than light, was the expansion of space itself. Inflation explains the universe's uniformity. The observable universe was once a tiny, causally connected patch. Microscopic quantum fluctuations were stretched to astronomical proportions, becoming the seeds of cosmic structure. The period of incredible exponential expansion could not last forever. After an incomprehensibly brief instant, somewhere around 10 to the minus 32 seconds, the inflationary era came to a sudden end. The mysterious energy field that drove the hyperexpansion known as the inflaton field decayed. It settled into a new lower energy state, and the rocket engine that had been driving the cosmos suddenly shut off. The universe's expansion did not stop entirely, but it slowed down dramatically, transitioning to the more moderate, steady expansion that continues to this day. The great inflationary growth spurt was over. The end of inflation marked another transformative moment for the cosmos. The immense energy that had been locked up in the inflaton field had to go somewhere. As the field decayed, it released its energy in a cataclysmic burst, flooding the now enormous universe with matter and radiation. This event is known as reheating. It was like a second Big Bang, but one that occurred everywhere at once throughout the vast, newly created space. The universe, which had become cold and empty during its rapid expansion, was instantly filled with a hot, dense, roiling soup of quarks, electrons, photons, and other elementary particles. This reheating process is what created the hot, dense state that is traditionally associated with the Big Bang. In a sense, the inflationary model reframes the story. The initial singularity is still the ultimate origin, but the hot, dense conditions that led to the formation of matter as we know it were actually established after inflation. This solves a major puzzle. Without inflation, it's hard to explain how the universe began in such a specific hot and dense state. With inflation, this state is a natural consequence of the inflaton field decaying and dumping its energy back into the cosmos, effectively resetting the stage for the next act. The universe was now vast, hot, and filled with the fundamental ingredients for everything that would follow. It was still a chaotic and unstructured place, a plasma of free-roaming particles, but the groundwork had been laid. The expansion was now proceeding at a manageable pace. The tiny density fluctuations magnified by inflation were now imprinted on the fabric of space-time, ready to act as gravitational seeds. The universe was primed and ready for the next phase of its evolution, the formation of the first protons and neutrons, the building blocks of every atom that would ever exist. The era of the quark soup had begun. Following the end of inflation and the reheating of the cosmos, the universe is about 1 microsecond old. That's 1/1,000,000th of a second. It has cooled down significantly from the earlier epochs, but the temperature is still an astounding 2 trillion degrees Kelvin. This is about 100,000 times hotter than the core of our Sun. Under these extreme conditions, the familiar particles of protons and neutrons still cannot exist. Their constituent components, the elementary particles known as quarks, are instead moving about freely in a state of matter known as a quark-gluon plasma. This state is often described as a perfect liquid. It is a dense, soupy mixture of quarks and the particles that carry the strong nuclear force called gluons. In our modern universe, quarks are always confined, locked together in pairs or triplets to form particles like protons and neutrons. They are never observed on their own. The strong force, carried by the gluons, acts like an unbreakable elastic band, pulling them back together if they try to separate. But in the immense heat of the early universe, the quarks had so much energy that they could overcome this confinement, roaming freely like individuals in a crowd. The universe at this stage is a sea of these fundamental particles. Quarks, antiquarks, electrons, positrons, neutrinos and photons are all constantly colliding, interacting and transforming into one another. The four fundamental forces are now all separate and acting in the ways we understand them today. Gravity is shaping the large-scale curvature of space-time. The strong force is mediating the interactions between the quarks and gluons, and the electroweak force has also split, meaning the electromagnetic and weak nuclear forces are now distinct. The universe has finally acquired its complete set of physical laws. This quark-gluon plasma is not just a theoretical concept. Scientists at powerful particle accelerators like the Large Hadron Collider at CERN are able to recreate the conditions of this epoch for tiny fractions of a second. By smashing heavy atomic nuclei together at nearly the speed of light, they can generate enough heat and pressure to momentarily melt the protons and neutrons, liberating the quarks and gluons and creating a tiny droplet of this primordial soup. By studying these experiments, we can gain direct insight into what the universe was like in its first microseconds of existence, testing our theories against hard physical data. As the universe continues to expand and cool, it approaches another critical threshold. At about 1 millisecond after the Big Bang, the temperature drops to a point where the quarks no longer have enough energy to roam freely. The strong nuclear force, which had been overcome by the intense heat, now becomes dominant. It acts like a powerful cosmic magnet, pulling the quarks together into stable bound states. Quarks begin to clump together in groups of 3, a process called hadronization. For the first time in cosmic history, stable protons and neutrons are formed. This was a dramatic and rapid transition. The universe changed from a fluid-like soup of individual quarks and gluons into a gas of newly formed composite particles. Every proton in the universe, including those in the atoms of your body, was formed during this moment. Each one consists of 2 up quarks and 1 down quark, bound together by the unyielding grip of the strong force. Similarly, neutrons composed of 1 up quark and 2 down quarks were also formed. The fundamental building blocks of atomic nuclei were now present in the cosmos, a monumental step toward a more structured universe. But remember that tiny imbalance from the very beginning, the 1 in a billion preference for matter over antimatter? This is where it becomes critically important. As the quarks combined, the antiquarks also combined to form antiprotons and antineutrons. For a short while, the universe contained a mixture of these matter and antimatter particles. But they quickly found each other and annihilated in a final massive burst of energy, leaving behind only the small surplus of matter. This is the great annihilation that left our universe with the material it needed for the future. After this, the era of antimatter's dominance was over for good. The universe was now filled with a hot gas of protons, neutrons, electrons, and a sea of photons and neutrinos. The frantic, chaotic dance of the first second was over. The fundamental laws and particles of the cosmos were now set. The stage was prepared for the next great act of creation, the forging of the first atomic nuclei. The universe was still incredibly hot and dense, but a semblance of order had emerged from the fire. The next few minutes would be crucial, determining the primordial chemical composition of the entire universe and setting the course for the formation of the first stars hundreds of millions of years later. We have just witnessed the birth of the first stable matter. The universe is now a few seconds old. The frantic, chaotic energy of the first moments has begun to subside, giving way to a slightly more orderly state. The driving force is the relentless expansion of space itself. This continuous expansion acts as a cosmic freezer, slowly lowering the temperature and allowing new structures to form. The early universe behaves like a steam engine releasing pressure, but on an unimaginable scale. This cooling is the engine of creation, guiding the universe from simplicity toward complexity. Each drop in temperature unlocks a new potential within the cosmos. The story of the early universe is a story of cooling, a tale of decreasing energy and increasing structure. To understand the universe, we must step back to a moment before the quark soup. We must discuss cosmic inflation. Occurring in a sliver of a second, this was a period of hyper-accelerated growth. A region smaller than an atom was stretched to a size larger than our galaxy. This idea solves mysteries of the Big Bang model, like the horizon problem. Inflation provides a simple solution. Before hyper-expansion, the observable universe was a tiny patch. All parts were in close contact, reaching thermal equilibrium. Inflation stretched this uniform region enormously. The uniformity we see is a magnified image of that initial patch. Inflation also explains the flatness problem by smoothing out any initial curvature. Inflation did more than just smooth out the universe and make it flat. It also planted the seeds of all future structure. This may sound like a contradiction, but it is at the heart of how our complex cosmos came to be. In the realm of quantum mechanics, even a perfect vacuum is not truly empty. It is a seething foam of quantum fluctuations, tiny, spontaneous variations in energy that bubble in and out of existence for fleeting moments. In the microscopic universe before inflation began, these quantum fluctuations were constantly creating minuscule ripples in the fabric of space-time itself. They were unimaginably small, far smaller than an atom. During the incredible stretching of inflation, these microscopic quantum ripples were themselves stretched to astronomical proportions. What was once a subatomic fluctuation became a wave of energy density that could stretch for millions of light years across the cosmos. This is the origin story of cosmic structure. These stretched-out fluctuations meant that after inflation, the universe was not perfectly uniform after all. It had vast regions that were infinitesimally denser than the average, and other regions that were infinitesimally less dense. The smooth canvas of the cosmos now had a subtle texture woven into it. These tiny density variations are the most important fossils we have from the first fraction of a second of time. They are the genetic code of the cosmos. The regions of slightly higher density, possessing a tiny bit more mass, would exert a slightly stronger gravitational pull. Over hundreds of millions and billions of years, this subtle extra pull would be enough to attract more and more matter. These were the gravitational seeds, the gathering points, around which the first stars, galaxies, and great clusters of galaxies would eventually form. The grand web-like structure of the universe is a direct, large-scale map of these quantum jitters from the first moment of time. Conversely, the regions that were slightly less dense would become the great cosmic voids. As matter was drawn toward the denser regions, it would evacuate these underdense areas, leaving them vast, dark, and empty. The existence of the cosmic web, this beautiful, intricate pattern of galaxy filaments and empty voids, is one of the most powerful pieces of evidence for the theory of cosmic inflation. We can see the statistical pattern of these fluctuations imprinted on the cosmic microwave background radiation. It is a breathtaking thought. The largest structures in our universe were born from the smallest scale randomness allowed by the laws of nature. The incredible rocket engine of inflation could not run forever. After that crucial fraction of a second, the mysterious energy field that powered it, the inflaton field, decayed. It settled into a stable, low-energy state, and the period of exponential expansion came to a screeching halt. The universe transitioned to the more moderate rate of expansion that we still observe today. But what happened to all the energy that was locked up in the inflaton field? It couldn't just disappear. Instead, it was released in a final cataclysmic burst that fundamentally reset the cosmic environment. This event is known as reheating. During the inflationary epoch, the universe had become phenomenally large, but also incredibly cold and empty. The pre-existing particles were spread so thinly across the vast new volume that space was effectively a vacuum. The reheating process changed all of that in an instant. The energy dumped into the universe by the decaying inflaton field spontaneously transformed into a torrent of matter and radiation, in accordance with Einstein's E=mc². The universe was instantly filled everywhere at once with a hot, dense, seething soup of quarks, electrons, photons, and all the other fundamental particles. In a very real sense, this was a second genesis for the universe. While the Big Bang singularity remains the ultimate origin of space and time, the hot, dense state that we typically associate with the fireball of creation was actually established after inflation, during this reheating phase. This neatly explains why the universe began in such a hot, dense state to begin with. It was the direct result of the end of inflation. The universe we know, a cosmos filled with matter and energy, was born from the ashes of the inflationary era. It was a fresh start on a stage that was now unimaginably vast. This new primordial soup was the starting point for all subsequent chemistry and physics. The temperature was set to trillions of degrees and the density was immense. It was from this reheated state that the quark-gluon plasma emerged, and from which the first protons and neutrons would eventually condense. The reheating phase connects the bizarre, exotic physics of inflation with the more familiar, though still extreme, physics of the hot Big Bang model. It is the crucial bridge between the moment that sculpted the scale and structure of our universe and the moment that filled it with the ingredients for stars and life. With the universe reheated, we find ourselves in a cosmos teeming with fundamental particles. This state existed for the first microseconds of time. It was a chaotic environment, a particle soup where matter and energy were in a constant state of flux. The primary residents were quarks, leptons and bosons. All of these particles were whizzing about at nearly the speed of light. The universe was a disassociated plasma of its most basic ingredients. The interactions were constant and violent. Among the most numerous particles were the photons, the particles of light. The early universe was awash with radiation. Through pair production, a single high-energy photon could transform into a particle-antiparticle pair. When an electron and a positron met, they would annihilate each other. The universe was a frantic equilibrium of creation and annihilation. In the early particle soup, for every particle of matter created, a corresponding particle of antimatter was also created. An electron came with a positron, a quark came with an antiquark. Antimatter is identical to matter in mass, but has the opposite electrical charge and other quantum properties. If the universe had maintained this perfect symmetry, our existence would be impossible. As the universe cooled, every single particle would have eventually found its antiparticle partner. They would have annihilated each other completely, leaving behind a universe filled with nothing but photons and other low-energy particles. There would be no matter left to form stars, planets or people. But we are here. The very fact of our existence proves that the perfect symmetry between matter and antimatter was broken. In the first moments of creation, a tiny, almost imperceptible imbalance must have occurred. For reasons that are still a subject of intense research in particle physics, the laws of nature showed a slight preference for matter. The leading theories suggest that for every billion pairs of matter and antimatter particles created, there was roughly one extra particle of matter. Just one in a billion. It was a minuscule cosmic rounding error, a slight imperfection in the mirror of creation. As the universe cooled below the threshold for pair production, the creation of new particle-antiparticle pairs ceased. What followed was the Great Annihilation, the final battle in the war between matter and antimatter. Particles and their antimatter counterparts found each other and vanished in countless flashes of light. The universe was engulfed in a final, furious blaze of energy. When the dust settled, the vast majority of both sides had been wiped out. All that remained was the tiny surplus of matter particles that had no antimatter partners to annihilate with. The one in a billion survivors. Everything we see around us today, every star in the sky, every rock on Earth, every atom in our bodies, is made from these leftovers. We are the fortunate survivors of a cosmic cataclysm. The light from all that annihilation, however, did not disappear. It became the dominant form of energy in the universe for a long time, contributing to the sea of photons that we now observe as the cosmic microwave background. The existence of a matter-dominated universe is one of the most profound clues we have about the fundamental laws of physics, pointing to subtle asymmetries that we are still striving to understand. The universe is now about 1 microsecond old. That's 1/1,000,000th of a second after the Big Bang. The cosmic freezer has continued its work, and the temperature has dropped to a mere 2 trillion degrees. This is a critical threshold. Below this temperature, the quarks that have been roaming freely in the primordial soup no longer have enough kinetic energy to escape the grip of the strong nuclear force. The gluons, which carry this force, now act like unbreakable cosmic glue. The universe undergoes another phase transition, a process known as hadronization, or the quark-hadron transition. The era of free quarks is over. In a rapid cascade across the entire cosmos, quarks are pulled together and confined into groups of 3 to form a new class of particles called baryons, Two up quarks and one down quark are bound together to create a proton. One up quark and two down quarks are bound together to create a neutron. For the first time, the stable building blocks of all atomic nuclei have been formed. The universe has transformed from a fluid-like plasma of elementary particles into a hot, dense gas of protons and neutrons, along with the still free-roaming electrons and photons. This was a monumental step towards structure. The properties of these new particles were now locked in. The proton, with its positive electric charge, and the neutron, with its neutral charge, would define the future of chemistry. Their relative masses and stability would play a crucial role in the minutes to come. Initially, protons and neutrons were created in roughly equal numbers, but a free neutron is slightly more massive than a proton and is inherently unstable, decaying into a proton, an electron, and a neutrino with a half-life of about 10 minutes. In the hot, dense, early universe, this decay was balanced by reactions that converted protons back into neutrons, maintaining a delicate equilibrium. As the universe continued to cool, however, the reactions that created neutrons became less frequent. The balance began to tip in favor of the more stable protons. The ratio of neutrons to protons started to drop. By the time the universe was about 1 second old, the ratio had fallen to about 1 neutron for every 7 protons. This ratio was now frozen in because the universe became too cool and sparse for the reactions to continue efficiently. This specific 7-to-1 ratio of protons to neutrons would have profound consequences, as it directly determined the chemical composition of the primordial elements that were about to be forged. The universe, just seconds old, becomes a nuclear furnace. In a brief window, protons and neutrons fuse to form the first light elements, deuterium, helium, and trace lithium. This process lasts only minutes before the universe cools too much for fusion to continue. The result, about 75% hydrogen, 25% helium, and tiny amounts of other light elements, ratios we still observe today. These primordial abundances are a cornerstone of Big Bang evidence. The universe is now a hot, dense plasma light cannot travel freely. Photons are trapped, endlessly scattering off free electrons, creating a glowing cosmic fog. For nearly 400,000 years, the universe remains opaque, with gravity and radiation locked in a stalemate. Matter cannot clump. The cosmos waits for temperatures to drop further. Only when atoms can finally form will the universe become transparent. At 380,000 years, the universe cools enough for electrons to bind with nuclei. Recombination. Neutral atoms form, the fog lifts, and light is set free in an event called decoupling. This ancient light, stretched by expansion, is the cosmic microwave background we detect today. The universe transitions from plasma to transparent gas, ending the cosmic dawn. Gravity now takes center stage, ready to shape the cosmos. With light liberated, the universe enters the cosmic dark ages. No stars, no galaxies, only darkness. Gravity slowly gathers hydrogen and helium into denser regions, aided by invisible dark matter. These dark matter halos act as scaffolding, drawing in gas and setting the stage for structure. For millions of years, the universe is a silent, dark expanse, patiently awaiting the first stars. The dawn is coming. Gravity, now unopposed, sculpts the universe. Gas clouds collapse and fragment, forming countless protostellar cores within dark matter halos. As these cores heat up, they become protostars, embryonic stars hidden in dense gas. When core temperatures reach 10 million degrees, nuclear fusion will ignite. The first stars are about to be born. The first stars, population 3, are massive, hot and short-lived, forged from pristine hydrogen and helium. Lacking heavy elements, these stars grow enormous, burning millions of times brighter than our sun. Their intense light ends the cosmic dark ages, illuminating the universe for the first time since the Big Bang's afterglow. These giants create the first heavy elements, seeding the cosmos for future generations. Their spectacular deaths will forever change the universe's chemistry. Deep inside a collapsing gas cloud, some 200 million years after the Big Bang, pressure and density increase. The core reaches 10 million degrees, Kelvin, hydrogen nuclei fuse, and a tremendous burst of energy occurs. Outward pressure counteracts gravity, halting the collapse. The star is born, shining a new light. After darkness, the universe lights up, one star at a time, ending the cosmic dark ages and beginning reionization. Bubbles of ionized plasma grow until the universe is once again an ionized plasma. The first stars were cosmic alchemists. Their cores were furnaces of creation, creating heavier elements in concentric shells like a cosmic onion. The star's core became a crucible, forging the building blocks of a more complex universe. This continues until the core is iron, a dead end. The star explodes in a supernova, briefly outshining a galaxy. Heavier elements are forged: gold, silver, platinum, uranium. The star scatters elements, enriching gas clouds for the future. The first stars were not born in complete isolation. They formed within the densest regions of the large dark matter halos that were collapsing throughout the universe. These halos were the gravitational cradles for all future structure. A single halo could contain enough gas to form not just one star, but millions. As the first massive stars exploded as supernovae, they seeded the surrounding gas with heavy elements. This had a profound effect on the next generation of stars. The enriched gas could cool much more efficiently, allowing it to fragment into smaller clouds and form smaller, longer-lived stars like our Sun. A new era of star formation began. Galaxies were not born fully formed like the grand spirals we see today. Instead, they were built up over billions of years through a process of hierarchical merging. The first objects to form were small proto-galaxies or dwarf galaxies containing perhaps only a few million stars. These were messy, chaotic collections of stars, gas, and dark matter. They were the building blocks of the larger structures to come. In the early, crowded universe, these small proto-galaxies frequently collided and merged with one another under the mutual pull of gravity. Each merger was a violent and spectacular event. When two galaxies merge, their individual stars rarely collide directly, as the distances between them are simply too vast. However, their enormous clouds of gas and dust slam into each other, triggering a massive wave of new star formation known as a starburst. These mergers are the primary engines of galaxy growth. Over cosmic time, countless such mergers between smaller galaxies gradually built up the larger, more massive galaxies we see in the universe today, including our own Milky Way. Our galaxy is not a pristine object, it is a composite, built from the cannibalized remains of many smaller galaxies over the course of 13 billion years. This process of galaxy formation was a cosmic construction project on the grandest possible scale. The dark matter halos provided the gravitational foundation. The primordial gas provided the raw building material. The first stars ignited the process and forged the heavier elements. Supernovae enriched the gas, allowing for new generations of stars. And the constant merging and colliding of smaller systems assembled these components into the vast, majestic galactic structures that now populate our universe. We live inside one of these structures, a testament to this long and violent history of cosmic assembly. As galaxies formed and grew through mergers, they were not distributed randomly throughout space. Their locations were dictated by the initial pattern of density fluctuations laid down during cosmic inflation. The galaxies formed within the massive dark matter halos, and these halos themselves were arranged in a specific large-scale pattern. Gravity caused these halos to stream along vast interconnected filaments like beads on a string. The universe on its largest scales began to resemble a gigantic three-dimensional spider's web. This grand structure is known as the cosmic web. The filaments of this web are immense, stretching for hundreds of millions of light years across space. They are the cosmic highways along which matter and galaxies travel. These filaments are made of dark matter and are threaded with warm intergalactic gas and chains of galaxies. They are the arteries of the universe, channeling material toward the great intersections where the filaments meet. These intersections are the most massive and densest nodes in the web. It is here that gravity's power is at its peak, and it is here that the largest structures in the universe are assembled, the great galaxy clusters. These galaxy clusters are the cosmic megalopolises. They are gargantuan collections of hundreds or even thousands of galaxies, all bound together by their immense mutual gravity. They are filled with a superheated gas that glows brightly in X-ray light, and they are dominated by a massive halo of dark matter. These clusters are the most massive, gravitationally bound objects in the universe, and they represent the culmination of the hierarchical structure formation process. They are still growing today, as more galaxies and smaller groups are pulled in along the cosmic filaments. The construction of the universe is an ongoing project. Between the filaments lie the great cosmic voids. These are vast, dark, and astonishingly empty regions of space. They are the areas that started out with a slightly lower density than the average. As matter was pulled toward the filaments and clusters, it evacuated these regions, leaving them behind as immense cosmic deserts. These voids can be hundreds of millions of light years across, containing very few galaxies. The stark contrast between the dense, bright filaments and the dark, empty voids is the defining characteristic of the large-scale structure of our universe, a beautiful and dramatic confirmation of our cosmological models. The universe has now been transformed. The cosmos has evolved into a place of breathtaking complexity and beauty. A rich and diverse ecosystem of stars and galaxies now populates the cosmos. There are grand spiral galaxies like our own Milky Way and massive elliptical galaxies. Inside these galaxies, the cycle of stellar life and death continues. Stars are born, live, and then they die. The most massive stars end their lives in spectacular supernova explosions, making the universe a more and more hospitable place over time. The universe is a place of dramatic contrasts, of light and shadow. The universe carries the memory of its own creation to create a structure of unimaginable richness from darkness to light. But the story is not over. Within this grand cosmic stage, an even more remarkable story is about to unfold. The death of the first stars was not an end, but a new beginning. Their supernova deaths seeded the cosmos with heavy elements like carbon, oxygen, nitrogen, silicon, and iron. These enriched clouds became the birthplaces for the next generation of stars, known as Population 2 stars. These clouds could now produce a wide variety of stars, including smaller, cooler, and longer-lived stars like our Sun. The new generation of long-lived stars provided the universe with time and stable environments. Furthermore, this new generation continued the cycle of cosmic enrichment, increasing the universe's metallicity, providing ever more of the raw materials needed to build rocky planets. As stars were born from clouds of gas and dust, they formed a rotating disk around the central star. This protoplanetary disk is the birthplace of planets. The universe contained the ingredients and environment for rocky planets to be assembled. Within this disk, planet formation began. Microscopic dust grains began to gently bump into each other and stick together, a process called accretion. These were the first true building blocks of planets. The composition of these new planets was determined by their distance from the central star. Rocky planets would form in the inner regions. Further out, beyond the frost line, gas giants could grow truly massive. About 4.5 billion years ago, our solar system was taking shape in the Milky Way. Among the protoplanets was a young, molten world, the Proto-Earth, constantly bombarded by asteroids. Early in its history, the Proto-Earth collided with Theia. A significant portion of Earth's mantle was blasted into space, forming a ring of debris. Over thousands of years, this debris formed our moon. This impact also tilted Earth's axis, creating seasons. Comets delivered water, while asteroids brought rock and organic molecules. The raw materials for oceans, continents, and perhaps even life itself were delivered to our young world. The universe is a vast chemical factory, producing a rich inventory of elements. For life, carbon is crucial. It can create an astonishing variety of complex and stable molecules. Oxygen, hydrogen, and nitrogen are also key. These elements form the primary chemical basis for all known life. They were forged in the hearts of stars and scattered across space by supernovae. The raw materials for life are natural byproducts of cosmic evolution, common throughout the galaxy. The cosmos is a fertile ground sprinkled with the seeds from which biological complexity can sprout. Having the right chemical ingredients is a necessary condition for life, but it is not sufficient. This narrow, temperate band around a star is known as the habitable zone. or the Goldilocks zone. Earth occupies a privileged position, orbiting comfortably within our Sun's habitable zone. It needs to be large enough to have sufficient gravity to hold onto its atmosphere and its oceans. The motion of Earth's liquid metal core generates a powerful magnetic field that surrounds our planet, acting as an invisible shield. Finally, the presence of plate tectonics has played a crucial role. It has kept Earth's climate relatively stable for billions of years. For centuries we speculated about planets beyond our solar system, but recently a revolution in astronomy has occurred. We've discovered thousands of exoplanets. The list of requirements for a life-sustaining world appears long. This has led to the rare Earth hypothesis, suggesting complex life like ours could be extraordinarily rare. Our Sun is stable. Our solar system has giant planets like Jupiter in stable orbits. Jupiter's gravity acts as a cosmic bodyguard. Are we the winners of an improbable cosmic lottery? The truth is, we don't yet know if we are a cosmic anomaly. Our story has focused on the matter we can see, but this entire drama has unfolded on a stage built by an invisible architect, dark matter. It makes up about 85% of all matter in the universe. It's completely invisible to our telescopes. We know it exists only through its gravitational influence. Without dark matter, we might not be here at all. It began to clump together long before normal matter could, forming vast, invisible halos. It dramatically accelerated the formation of the first stars and galaxies, creating the galactic environments where stars, planets, and life could emerge. Our existence is fundamentally tied to this enigmatic, invisible component of the cosmos. As we look back on this grand cosmic journey, a remarkable picture emerges. From the Big Bang to our solar system, the universe has undergone a profound transformation, guided by the fundamental laws of physics. This has led some to ponder the fine-tuning of the universe. It seems we live in a Goldilocks universe, where the fundamental parameters are just right for our existence. Why is this so? We are the universe made self-aware, the means by which the cosmos can look back upon itself. Our journey through cosmic history brings us back to the human spirit of inquiry. This drive to know our origins is a deep echo of the Big Bang itself. It compels us to seek our place in the grand cosmic narrative, connecting us to our ancestors. The desire to comprehend the cosmos is a universal human trait, manifested in myths and creation stories. Though methods change, the motivation remains, to replace darkness with understanding. We are not the center of the universe, yet this cosmic demotion has endowed us with profound significance. We are the universe's memory, its consciousness, its voice, piecing together our cosmic origins. Our cosmic origin story is inseparable from our tools. The telescope, a revolutionary invention, shattered the old worldview. We discovered vast galaxies millions of light years away. Galaxies are rushing away from us. The universe is expanding, evidence for a Big Bang. Space telescopes are true time machines. The Hubble and James Webb Space Telescopes allow us to peer deep into the cosmic past. We witness the cosmic dawn, watching as the first galaxies ignite. We test our ideas against the reality of the past, written in ancient light. Telescopes gather data, but mathematics interprets it. The universe's story is written in light and equations. Einstein's relativity described gravity as space-time curvature, predicting an expanding universe before it was observed. Mathematics models reality, enabling us to explore the unexplorable. Light is a messenger. Spectroscopy reveals a source's chemical composition. Redshift measures a galaxy's recession speed. The cosmic microwave background tells the infant universe's story. Decoding light reveals the universe's secrets. Humanity's journey to understand its origins has been, well, a journey from myth to measurement. For millennia, our creation stories were powerful, poetic narratives that provided meaning and a sense of place. They were the best explanation possible with the tools at hand: observation, intuition, and storytelling. These myths were not science, but they served a similar human need to make sense of the world and our existence within it. They were the first draft of our cosmic history, born from the same wellspring of curiosity that drives scientists today. The methods have evolved, but the fundamental question remains unchanged. the scientific revolution marked a profound shift in our approach. The new paradigm insisted on a different kind of evidence. It demanded ideas that were not just satisfying, but testable. It required theories that could make specific quantitative predictions, which could then be verified or falsified by experiment and observation. This disciplined approach, the scientific method, has allowed us to build a creation story of a completely different kind. Our modern cosmological model is not a static story handed down through generations. It is a dynamic, living theory, constantly being refined and challenged by new data. This transition has led us to a story far more wondrous and strange than any of our ancestors could have imagined. Who could have dreamt of a universe born from a point of infinite density, a period of exponential expansion faster than light, or that every atom of carbon in our bodies was forged in the heart of a dying star? The reality revealed by science is more awe-inspiring than any myth. It has shown us a universe of immense scale and antiquity, governed by elegant and powerful laws that we are capable of discovering and understanding. This is the triumph of the human intellect. Our modern creation story, the Big Bang Theory, is now supported by multiple independent pillars of evidence. The expansion of the universe, the existence and precise temperature of the cosmic microwave background, the observed abundances of the primordial light elements, and the formation of large-scale structures like the cosmic web all point to the same inescapable conclusion. Our universe began in an incredibly hot, dense state and has been expanding and cooling ever since. We have replaced the poetry of myth with the precision of measurement, and in doing so have uncovered a story of our origins that is all the more powerful for being true. Our journey has brought us an incredible distance, but it has also brought us to the edge of a vast ocean of mystery. For all that we know, there is still so much that we do not. The very beginning of our story, the moment of the Big Bang itself, remains shrouded in enigma. Our theories of physics, both general relativity and quantum mechanics, break down at the extreme energies and densities of the singularity. We have no reliable way to describe what happened at time zero, or to answer the profound question of what, if anything, came before the Big Bang. This is really the ultimate wall, a frontier that awaits a new revolution in physics. The incredible period of cosmic inflation, which so elegantly explains the flatness and uniformity of our universe, is another great mystery. While the evidence for it is strong, the physical mechanism behind it remains elusive. What was the inflaton field that drove this hyper-expansion? What is the fundamental physics that governs it? Answering these questions is a primary goal of modern cosmology, as it would give us insight into the universe at an energy scale far beyond anything we can replicate on Earth. Understanding inflation is key to understanding the very first moments of time after the initial singularity. Another deep puzzle lies in the profound imbalance between matter and antimatter. Our theories predict they should have been created in equal amounts, leading to their complete annihilation and a universe filled only with light. And yet here we are, made of matter. A tiny 1 in a billion asymmetry in the early universe allowed matter to survive. What physical process caused this crucial imbalance? The answer is thought to be hidden in subtle differences between the behavior of matter and antimatter. But the exact mechanism remains one of the most significant unsolved problems in all of particle physics and cosmology. These are what we might call the known unknowns, the questions we know how to ask but do not yet have the answers for. What is the nature of the singularity? What drove cosmic inflation? Why is there more matter than antimatter? Each of these questions represents a frontier of human knowledge, a challenge for the next generation of scientists and thinkers. Our current understanding is a magnificent achievement, but it is also an island in a vast sea of ignorance. The search for answers to these profound questions will drive the next great leaps in our comprehension of the cosmos. We've only ever seen a tiny fraction of what the universe is made of. All the normal matter accounts for only about 5% of the total mass and energy. The other 95% is the dark universe. About 27% is dark matter, the invisible scaffolding upon which cosmic structure is built. We can see its gravitational effects. Even more mysterious is dark energy. which makes up 68% of the universe. It is accelerating the expansion of the universe. We have almost no idea what it is. Dark matter and dark energy represent a monumental challenge to our understanding of physics. Unraveling their nature could revolutionize our understanding of the universe's destiny. Our journey has shown us a universe that seems ripe with potential for life. We have seen how the laws of physics give rise to stars, how stars forge the chemical elements necessary for biology, and how these elements coalesce into planets. In our own galaxy alone, there are hundreds of billions of stars, and we now know that most of them have planets. The number of potentially habitable worlds in the Milky Way could be in the tens of billions. This staggering number leads us inevitably to one of the most profound and tantalizing questions we can ask. Are we alone? For all of cosmic history, as far as we know, the universe was a lifeless place. Then, on at least one small planet, in an unassuming corner of one galaxy, something remarkable happened. Life emerged. It has flourished and diversified, and eventually it produced a species capable of contemplating its own existence and asking this very question. Is this a common occurrence? Is the universe teeming with life, a cosmic garden filled with countless species on countless worlds? Or is the spark of life an exceedingly rare accident, making our planet a unique and precious oasis in a vast sterile desert? This question has launched a dedicated scientific search. Programs like SETI, the Search for Extraterrestrial Intelligence, have spent decades using powerful radio telescopes to scan the skies, listening for any signal that could betray the presence of another technological civilization. So far, the search has been met with a profound and deafening silence. This great silence, as it is sometimes called, is a deep puzzle. If life is common and if some of it evolves intelligence, why do we not see any evidence of it? Where is everybody? This is the Fermi paradox, and it has no easy answers. Perhaps civilizations are rare, or they do not last long enough to be detected. Perhaps the distances between the stars are simply too vast to overcome. Or perhaps we are simply not listening in the right way. Whatever the answer, the question of our cosmic solitude remains one of the greatest drivers of our exploration. The discovery of even simple microbial life on another world, such as Mars or a moon of Jupiter, would be one of the most significant moments in human history. It would tell us that the origin of life is not a unique fluke, and that the universe we inhabit is not just a cosmos of physics and chemistry, but one of biology as well. Our exploration of the universe's birth has been a journey of epic proportions spanning 14 billion years of time and the entire expanse of space. We have seen a universe born from an infinitesimal point, evolve through fire and darkness, and blossom into a complex and beautiful cosmos filled with stars, galaxies, and at least one world teeming with life. We have seen how humanity, through its relentless curiosity and ingenuity, has managed to piece together this incredible story, tracing our own lineage back to the very first moment of creation. It is the greatest story ever told because it is the story of everything. This story is a testament to the power of the human mind and spirit. It shows that even though we may be physically small and our lives fleeting, our ability to understand is boundless. We have used reason, mathematics and observation to transcend our limitations and grasp a reality far beyond our immediate senses. The journey has been humbling, revealing our cosmic insignificance, yet also empowering, revealing our unique position as the universe's self-aware observers. We are the children of the stars, and we have finally begun to read the family history. But this story has no final chapter. Our quest for understanding is a never-ending journey. Every answer we find only opens up a new landscape of deeper and more profound questions. The end of one journey of discovery is simply the starting point for the next. The mysteries of dark matter, dark energy, the origin of life, and the ultimate fate of the cosmos still await us. There will always be new horizons to explore, new puzzles to solve, and new wonders to uncover. The universe is a book of infinite pages, and we have only just begun to read the first few. So let us continue to look up. Let us continue to question, to explore, and to wonder. The same curiosity that drove our ancestors to chart the stars now drives us to build new telescopes, devise new theories and search for life on other worlds. The journey is far from over. In a very real sense, it has just begun. The universe has been patient with us, waiting 14 billion years for conscious minds to emerge and appreciate its splendor. The future of our understanding is limited only by our imagination and our will to continue the search, to keep turning the pages of the great cosmic